chapter units and measurement exercises. First question, filling the blanks. The volume of a cube of side 1 centimeter equal to, in meter cube you need to find. So centimeter is 10 power minus 3, 10 power minus 2 meter, 1 centimeter. So you need to take cube of it. When you take cube, you will get the answer 10 power minus 6 meter cube. Then the surface area of a solid cylinder of radius 2 centimeter and height 10 centimeter is equal to, in millimeter square you need to calculate. First of all, we have 20 millimeter and 100 millimeter. The quantities we can convert into millimeter. Then total surface area of the cylinder we have to calculate. Surface area of the cylinder is, we have two cross sections having area pi r square each, plus we can have the curved part of the cylinder. So 2 pi r is the breadth of the curved part and h is the length of the curved part, and you can calculate the answer by substituting these values both in millimeter, so that you will get the answer in millimeter square. Then a vehicle moving with a speed 18 km per hour covers hash meter in 1 second. So kilometer per hour you have to convert into meter per second, and is 18 into 5 by 80. Kilometer per hour we can convert into meter per second by multiplying 5 by 18, so that you get the answer 5 meter in 1 second. Then the relative density of lead is 11.3. Its density is in gram per centimeter cube or kilogram per meter cube. So density of the substance, rho is equal to relative density into density of water is equal to, relative density is given 11.3. Density of water is in CBSE system is 1. Therefore, you will get the answer 11.3 gram per centimeter cube. Now, either we can take relative density of water in SI system is 1000, or you can convert this gram into kilogram and centimeter cube into meter cube, so that you will get the answer that is equal to 11.3 into 10 power 3 kilogram per meter cube. Now, question number 2, fill in the blanks with suitable conversion of units. First one, 1 kilogram meter square per second square is equal to how many grams centimeter square per second square? Kilogram meter square per second square means it is joule. So gram centimeter square per second square is erg. So you can write kilogram in gram, meter square in centimeter square. Then unit of time is same in both the system. So you will get the answer 10 power 7 gram centimeter square per second square. Next, 1 meter is how many light years? There You can see that 1 light year is 9.46 into 10 power 15 meter. 9.46 into 10 power 15 meter is 1 light year. So just cross multiply it so that 1 meter is equal to 1 divided by 9.46 into 10 power 15. So you will get approximately 10 power minus 60 light year approximately. Then next we can have 3 meter per second square. You have to convert into kilometer per hour square. So we can have 3 meter per second square is equal to 3 meter. First of all, you can convert into kilometer. 3 into 10 power minus 3 kilometer. Then divided by second square, we have to convert into hour. When you convert second into hour, you have 1 by 60 into 60. Now here we have second, so second we can convert into hour by 1 divided by 60 into 60. Now here we have second square is there, so our square. So simplify and find the answer. Then next, G equal to 6.67 into 10 power minus 7 Newton meter square per kilogram square, and we are asked to convert it into centimeter cube per second square per gram. Okay, so here first of all we can take this unit Newton meter square per kilogram square, and Newton meter square per kilogram square can be written as kilogram meter per second square, that is Newton, into meter square divided by kilogram square. So when you simplify, you will get a meter cube per second square per kilogram. Quantities, meter cube you can convert into centimeter cube. Second square, there is no change required. Per kilogram, kilogram is in denominator, you can convert into gram. Then multiply with this quantity so that you will get the answer. Now next, question 3. Calorie is a unit of heat or energy. It equals 4.2 joule. 4.2 joule. And 1 joule already, kilogram, 1 kilogram meter square per second square. Now we have a new system of units in which unit of mass is alpha kilogram, unit of length beta meter, and unit of time gamma second. So this is a new system of unit with the fundamental units having alpha kg, beta meter, and gamma second. Now show that 4.2, the new system, it is 4.2 alpha raised to 1, beta raised to minus 2, and gamma square. Means it's a question for unit conversion. And we know the unit conversion formula, that is N1U1 is equal to N2U2 is the unit conversion formula. Here dimensions is energy. So we know the dimensions of energy. We have M L square T minus 2 is the dimensions of energy. For the system, we can take here as N1 into, we have M1 L1 square t raised to minus 2, t1 raised to minus 2 is equal to n2 L2 square t raised to minus 2, t2 raised to minus 2. Now, n1 is given in the question. N1 is equal to 4.2 Joule. 4.2. N2 we have to find out how much is N2. So here you can cross multiply the equation. N2 is equal to 4.2 into 4.2 into M1 divided by N2 into L1 square divided by L2 square into T1 by T2 raised to minus 2 is equal to 4.2 into M1, we know it is kilogram, while M2 is alpha kilogram according to the question, into L1 is meter, L2 is beta meter power 2 into T1 is second and T2 is gamma second raised to minus 2. So equal to 4.2 into here kilogram and kilogram gets cancelled. Alpha goes to numerator, so alpha raised to minus 1. Here meter cancel and beta goes to numerator, so beta raised to minus 2. Here second cancel, gamma raised to minus 2 will come. When it goes to numerator, it becomes gamma raised to plus 2. And this is what you are asked to prove there. Now, next, question 4. Explain this statement clearly. To call a dimensional quantity large or small is meaningless without specifying standard for comparison. Okay, so we have here N1 numerical value U1 unit is equal to N2 the numerical value for conversion into U2 unit. So here the product of NU is a constant. That is why you are getting the product of N1 U1 which will be equal to N2 U2. If you have another unit, then it will be equal to N3 U3 like that. Therefore, we can say N inversely proportional to U. What is the meaning of that? If unit is big, U is big, N is small. If unit is small, then N will be large. This we used to explain with a simple example. 1 meter is equal to 100 centimeter. There you can see the unit centimeter is small, then the numerical value is 100. It is big. The unit meter is big. It's a big unit compared to centimeter. Then the numerical value is small. So we can say they are inversely proportional. The same only given in the statement of the question. That is, whenever you can have a large quantity, we can say large or small, which depends on in which unit we have expressed the same. Okay, from this example, you can understand it clearly. Now, next, a new unit of length is chosen such that the speed of light in vacuum is unit. What is the distance between the sun and the earth in terms of the new unit if light takes 8 minutes and 20 seconds to cover this distance? That means to reach over the earth. So distance we can take, distance is equal to speed into time. You can substitute the values. Speed of light is 3 into 10 power 8 into time 8 minutes 20 seconds. You have to convert into second. You will get approximately 500 seconds. Now in the new system of unit, system of unit, speed of light is taken as unit 1. That means 3 into 10 power 8 is taken as 1. And if 3 into 10 power 8 is 1, then this equation we have to write 1 into 500. 1 into 500. So then what is the answer? You will get the answer that is equal to 500 units. Just like we take a 500 centimeter like that, 500 units in the new system of units. So answer is 500 units. Now question 6, which of the following is the most precise device for measuring length? A vernier calibrates with the 20 divisions on the sliding scale. 20 divisions on the sliding scale means we can understand 1 millimeter is divided into 20 parts. 1 millimeter is divided into 20 parts. Then a screw gauge of pitch 1 millimeter and 100 divisions on the circular scale. So, which means 1 millimeter is divided into 100 parts. 1 millimeter is divided into 100 parts. Then see an optical instrument that can measure length within the wavelength of light. Within the wavelength of light means 1 millimeter. Now, average wavelength of light you can take as 10 power minus 6, which means here 1 millimeter is divided into 10 power 6 parts. So now go back to the question, which of the following is the most precise device? You can give a precise in the sense here we have to see maximum precision. Definitely, okay, 1 millimeter is again and again divided. You can see here 10 power 6 times. Therefore, option C is the correct answer. Now, next question 7. Student measures thickness of human hair by looking at it through a microscope of magnification 100, which means magnification M is equal to 100. Then he makes 20 observations and finds that the average width of the hair in the field of view of the microscope is 3.5 mm, which means the size of the image H dash 3.5 millimeter. What is the estimate on the thickness of the hair? You know the formula, M is equal to H dash by H. Cross multiply the equation and find the value of H, the size of the object. Question 8. Answer the following. You are given a thread and a meter scale. How will you estimate the diameter of the thread? You know, it's not possible to estimate the diameter of the thread using a meter scale, because a meter scale is having millimeter markings and centimeter markings. But the question is there any possibility, okay, for doing so? That's the question. So we can think about a method like this. So we can have the centimeter scale. Now at the centimeter scale, okay, so you take the given thread and wind the thread around the scale like this. Okay. So in this way, make the windings, tight windings over the scale in such a way that each winding is in contact. So like this, the windings are like. Suppose this is from 0. You have started the winding, and the windings got over at 5 centimeter. 5 centimeter. Now the total length of the windings, 5 centimeter. Now count the number of windings. So this 5 centimeter I will take as L. Now count the number of windings which I will take as N. Now you see what will be the thickness of each winding. You can calculate the thickness of each winding by taking L by N. Total length divided by number of windings. And thickness of the winding means it is the diameter of the thread. So by taking L by N, total length of the windings divided by number of windings, the diameter of each winding, that means diameter of the threads, can be calculated. Now, part B, a screw gauge of pitch 1 millimeter and 200 divisions on the circular scale. Do you think it is possible to increase the accuracy of the screw gauge arbitrarily by increasing the number of divisions on the circular scale? Okay, so here we can have 1 millimeter pitch and 200 divisions. It means 1 millimeter is divided into 200. Okay, now suppose arbitrarily we can increase the number of divisions on the circular scale. Suppose it becomes 500, imagine. Which means 1 millimeter is divided into 500 parts. Then what happens? Naturally, the accuracy of the measurement will increase. Okay, so answer is yes, it is possible. Next, the mean diameter of a thin brass rod is to be measured by vernier calipers. Why is a set of 100 measurements of the diameter expected to yield a more reliable estimate than a set of 5 measurements only? So you have two options. You can take 100 measurements and you can take 5 measurements. So your question is, do you expect 100 measurements is can give more reliable answer? Of course, because when you take 100 measurements, you know our method to calculate the true value. We used to take the average of all measurements. Okay, so when you take 100 measurements, definitely you will get a more correct average value or more correct true value. So if you take 100 measurements, it can yield better true value of the measurements. Now, next, a photograph of a house occupies an area 1.75 centimeters square on a 35 mm slide. The slide is projected on a screen and the area of the house on the screen is 1.55 meters square. What is the linear magnification of the projector on the arrangement? So look at here. We can have a rectangle. Now that rectangle, just assume that now you have observed it through a lens and you can observe the rectangle like this. So we have L, B, and here you can have B dash. B dash is equal to MB, because magnification M, you know, B dash by B is equal to M. Similarly, here we can have L dash is equal to ML. Again, linear magnification M is equal to L dash by L, size of the image divided by size of the object. Now here you can calculate the area. Area A is equal to L into B. Now in the second case, we can calculate the area. Area A dash is equal to area of the image. A dash is equal to L dash into B dash is equal to ML into MB is equal to M square into LB is equal to M square into LB is again A. Therefore, we can have A dash by A. Area of the image divided by area of the object is equal to M square, or M is equal to, that is M is linear magnification, M is equal to under root A dash by A, under root A dash by A. Size of the image is given 1.55 meter square. Size of the object A is given 1.75 centimeter square, which you need to convert into meter before substituting in the equation. And using the formula, you can calculate the value of linear magnification. Now, next, state the number of significant figures in the following. You need to apply the rules. That's only. First case you will get 1. Second case you will get 3. Third case 4. Fourth case again 4. Fifth case 4. And the last one again 4. Then next, question 11. Length, breadth and thickness of a rectangular sheet of metal values are given. Okay. Then give the area and volume of the sheet to correct significant figures. Okay. So volume formula, V is equal to LBH. Substitute the values and find the answer. And when you find the answer, you have to apply the rule of significant figures in the product. Now, next, area. Area is equal to 2 into LB plus LH plus BH equal to. Can substitute the values and find the answer. But when you find the answer, again you have to see, when you take these three products, you have to use the rule of significant figures for the product. Then afterwards, when you add the three quantities, you have to use the rule of decimal points. Then find the final answer. Now, question 12. The mass of a box measured by Rose's balance is 2.300 kilogram. Two gold pieces of masses 20.15 gram and 20.17 gram are added to the box. What is the total mass? So what you have to do first, you have to convert these two, 0.02015 kilogram, and the second one is 0.02017 kilogram. Then you have to add these two quantities with 2.300 kilogram. Then you know that the final result should retain. It is an addition. The least number of significant digits in the numbers which you have added. Follow that rules. And the difference in masses of two pieces of to correct significant figures. Difference in mass means you can do it in gram itself, no problem. You will get a 0.02 gram because you have two decimal points there. You have to use the rule of decimal points in subtraction. Now question 60. Unit of length convenient on an atomic scale is known as an angstrom and is denoted by, you can see angstrom symbol. One angstrom is 10 power minus 10 meter. The size of hydrogen atom is about 0.5 angstrom. The size of hydrogen atom, we can take it as radius of hydrogen atom is 0.5 into 10 power minus 10 meter. What is the total atomic volume in meter cube of 1 mole of hydrogen? So for one hydrogen atom, the volume assumed to be spherical, okay, 4 by 3 pi r cube. Then you are asked to 1 mole of hydrogen atom. So in 1 mole of hydrogen, you know, Avogadro number of atoms will be there. So into Na, Avogadro number, you know, 6.02 into 10 power 10 power plus 23, that you have to multiply here. You will get the answer. Then question 17. 1 mole of an ideal gas at standard temperature and pressure occupies 22.4 liter, which we call the name molar volume. What is the ratio of molar volume to the atomic volume of a mole of hydrogen? Again, the size of hydrogen molecule. Remember, this is hydrogen molecule. The size of hydrogen molecule is 1 angstrom. Okay. Why is this ratio so large? So here, just consider 1 mole. This is a volume of 1 mole, which we call the name molar volume, and that molar volume is 22.4 liter. That means this box has a volume 22.4 liter. Now this box is occupied by hydrogen atoms like this. Hydrogen atoms are there. Now, when you calculate the actual volume of hydrogen, what is the actual volume of hydrogen molecules? Only this volume of these PS only you need to consider for getting actual volume, as we have calculated in the previous question. So there it was, hydrogen atom. Here we have to take hydrogen molecule. That's the difference. Okay. Anyway, you can see in 1 mole we have Avogadro number of molecules are there. Therefore, the atomic total volume of actual volume of hydrogen we can take as V is equal to, for 1 molecule it is 4 by 3 pi r cube. R you have to take as 1 angstrom, that means 10 power minus 10 into total number of molecules in 1 mole, that is Avogadro number. Now, how much is molar volume, the total volume of the box where these molecules are occupied? That is molar volume, which I will write as Vm is equal to 22.4. It is given in liter, so 10 power minus 3 meter cube. 1 liter is 10 power minus 3 meter cube. Now you are asked to take this ratio, which is Vm divided by V. So you can substitute the values and find the ratio. Now, why is this ratio so large? The ratio is very large means this molar volume of the box is much greater than the actual volume of the molecules. So what is the reason? Because you know the density of gas is very less. Lot of empty spaces in between the gas molecules. very low density. Gas has very low density. So here all you have a lot of empty spaces. So compared to the volume of the box, the actual volume of the molecules will be much less. Okay, now question 18. If you look out of the window of a fast-moving train, the nearby trees, houses, etc. seem to move rapidly in a direction opposite to the train's motion. But the distant objects, hilltops, the moon, the stars, etc., seem to be stationary. In fact, since you are aware that you are moving, these distant objects seem to move with you. Okay. So, what is the question? You can take two objects of same size. Okay. For example, okay, you can imagine two trees of height h, something like that. Now, or between 2 points you can take. If the object is close to you, then you can see always from your eyes, you are observing at an angle. An angular view is there. So when the object is close to you, because it is a tree which is close to you, then it makes an angle theta 1. While the tree that of same size is far away from you, you can see your angular view, angle subtended at the eye is theta 2. Now assume that you observe both of them during the same time interval. In the case of the object close to you, you can write its velocity or we can say the speed. Okay, that will be better. The speed of the first object, you can take speed is equal to theta 1 divided by first object, theta 1 divided by t. While for second object, v2 is equal to theta 2 divided by t. You see there, the angle subtended at the eye for the nearby object, theta 1, is much greater than the angle subtended by the same object if it is far away from you. As theta 1 is greater than theta 2, we can say v1 greater than v2, which means you will observe the speed of the nearby object is much greater than the speed of the distant object in their relative motion what you observe. Then next, again how the question gives the definition of parsecond. A parsec is a convenient unit of length on the astronomical scale. Okay, it is the distance of an object that will show a parallax of 1 second of r from opposite ends of a baseline equal to distance from Earth to Sun. Okay, so we can have a Sun. Then around the Sun we can have the Earth's orbit. So here we have Earth, then radius of Earth orbit. Now what is parsec according to the question? We need to take an object here. Take an object. And this particular object will make an angle, and that angle should be 1 second. Angle is 1 second, provided the baseline equal to distance from the Earth to Sun. This baseline is the distance from Earth to Sun. Distance from Earth to Sun means you can see it is the average radius of Earth's orbit. So according to the definition, this distance, okay, we can take it as t. Distance d is parsec, and under the condition that this angle is 1 second and the baseline is the distance between Earth and Sun. Okay, in such a situation, so you have to calculate the parsec d. You need to calculate how to find the parsec d. We have the formula: angle theta is equal to arc length r divided by radius. So here d will be the radius. So we need to calculate d parsec. D is equal to r divided by theta is equal to, it is given diameter of Earth's orbit is 3 into 10 power 11. So how much will be the radius? 1.5 into 10 power 11 divided by theta is 1 second. 1 second you have to convert into SI unit. So we can have 4.9 into 10 power minus 6 radian. So from this calculation only you will get it. So d is 1 parsec. So you will get a 1 parsec is equal to 3.06 into 10 power 16 meter. Then next question 20. The nearest star to our solar system sorry, is 4.29 light years away. 4.29 light years away. How much is this distance in terms of parsec? So what can be done? First of all, the distance d we can calculate in meter. So 4.29 light year means 4.29 into 9.46 into 10 power 15 meter. And 1 parsec we know that it is 3.06 into 10 power 16 meter. Therefore, you will get this distance in parsec by dividing 3.06 into 10 power 16. So that many parts. Then next, there is a second part for that question. How much parallax would this star named Alpha Centauri show when viewed from two locations of the Earth 6 months apart in its orbit? How much parallax? Parallax means you need to calculate parallactic angle. Theta is equal to arc length divided by radius. Arc length divided by radius. And here it is given two locations of Earth 6 months apart. 6 months apart means you can see in this diagram here 6 months apart means it is the diametrically opposite position. That means how much will be the baseline? Baseline will be the diameter of Earth's orbit. Diameter of Earth's orbit we have seen in the previous question. That is 3 into 10 power 11 is the diameter. Then distance in meter we have to substitute. The distance we know in meter, here it is 4.29 into 9.46 into 10 power 50. So simplify, you'll get the answer. Now question 21 and 22 you can leave. Question 23, the quantities we can see there. we have mass of sun, radius of the sun, and you have to calculate density of the sun. You know the formula, density is equal to mass by volume. And substitute the values and you can find the answer. Then the question says that in what range do you expect the mass density of the sun to be? In the range of densities of solids and liquid or gases. As far as our knowledge, the sun is made up of hydrogen and helium gas, the main content of the sun. But you know, here when you calculate the density, you will get the density in the order of rho in the order of 10 power 3 kilogram per meter cube. And 10 power 3 kilogram per meter cube means it is the order of density of solids. Okay. But we believe that the main constituent of the sun is just different types of gases, mainly hydrogen and helium. So then how do you get an answer which is in the range of solid densities? We believe that the gravitational force in the sun is very, very high, extremely high. So that what happens? The gas is at highly compressed stage. As the gases are at a very highly compressed stage, its density will be in the order of density of solids. That is the reason you get the answer in this particular range. Now, next question 24. Planet Jupiter at a distance 824.7 million kilometers. You have to convert into meter. So you can have 824.7 first of all million 10 power 6, then kilometer per to meter 10 power 3. Then angle is given, theta is equal to 35.72 seconds. Calculate the diameter of the Jupiter. Diameter of the Jupiter we have to calculate. Okay, the situation is like this. Imagine Jupiter, then distance, then diameter of the Jupiter. Now, diameter of the Jupiter, capital D, you have to calculate. This distance is given, this angle is given. So again, use the formula. Theta is equal to capital D, diameter divided by small d, according to our diagram. Cross multiply the equation, diameter of the Jupiter is equal to theta into d. Substitute the values here. Theta also, first of all, you have to convert into radian. Then you have to substitute here to get the final answer. Then next question 25. A man walking briskly, okay, rain, he is holding an umbrella. So here the relation, the formula, theta is equal to V is equal to tan theta. Okay. Then whether this equation is correct or not, tan theta is equal to V. This kind of question we have done in chapter one-dimensional motion, at what angle the umbrella should be held, etc. Whether this equation is correct or not. This equation is not dimensionally correct because tan theta has no dimension, but velocity V has dimensions. So you remember in those problems which we have seen in the chapter one-dimensional motion, tan theta is equal to V divided by V dash we have to take. V divided by V dash. Okay, so where V dash is the velocity of the ray, like that we have to take. So now in this formula will be correct. So V by V dash, both speed divided by speed becomes dimensionless and the equation becomes correct. Now question 26. It is claimed two cesium clocks, if allowed to run for 100 years time, 100 years, free from any disturbance, may differ only about 0.02 seconds. That means 0.02 seconds in 100 years. Okay. Then what does this imply for the accuracy of the standard cesium clock in measuring a time interval of 1 second? So now you can calculate delta t divided by t. Delta t is 0.02 seconds and t 100 years. 100 years you have to convert into seconds into 365 into 24 into 60 into 60. So find the answer. And about the quotient, we have discussed that whenever you calculate a quotient, actually we are calculating how much you are getting out of 1. So here when you take delta t by t, actually you are getting out of 1 second what is the variation. So by calculating this, you can see that for 1 second the variation is in the order of 10 power minus 12. 10 power minus 12. For which you have to solve this, then you will get nearly 10 power minus 12. And it indicates that for 1 second, the variation will be around 10 raised to 12. 1 by 10 raised to 12 will be the variation that happens. 1 by 10 raised to 12 means, it's a very, very small quantity that happens in 1 second or 100 years. 1 by 10 raised to 12 variation will happen in 1 second over 100 years. Then next, question 27. Estimate the average mass density of sodium atom. The size of the sodium atom is given to 0.5 angstrom, which you can take as the radius. Okay. So how can you calculate? Here we have mass of 1 mole. 1 mole means Avogadro number of sodium is 23 gram. It's molar mass, which means 23 into 10 power minus 3 kilogram. That is the molar mass of sodium. Therefore, mass of 1 sodium atom, mass of 1 sodium atom. For Avogadro number of molecules, we have 23 into 10 power minus 3 kilogram. For 1 atom divided by Avogadro number is the mass of 1 sodium atom. Then we are asked to calculate density. Rho is equal to mass divided by volume. Volume you can calculate using the formula V is equal to 4 by 3 pi r cube. Assuming to be spherical, first find the volume. Then you can find mass also. Once you get the mass and volume, then you can find the density of sodium atom. Compare with the density of sodium in its crystalline phase, that is 970 kilogram per meter cube. So when you compare, you can see that you will get a very high density here. For the density of atom will be high, but density of the crystal will be less. So again, you can see there is a tight packing. So that is the reason you will get a high densities. A tight packing is there. The particles are packed tightly there. Now, next, one Fermi, 10 power minus 15 meter. Then there is a relation or radius of a nucleus and the mass number. A is the mass number. You know, mass number is the number of nucleons, the sum of the number of protons and neutrons. So this is a relation connecting radius of the nucleus and mass number. R is equal to R naught A raised to 1 by 3, where R naught is a constant. And value of that constant is 1.2 Fermi is the value of the constant. Now you are asked to prove the nuclear density is nearly constant for different nuclei. Which means if you take hydrogen or if you take sodium or if you take uranium, all of them having nearly same densities, which you need to prove here. Okay, here, first of all, we assume that the mass of protons is approximately equal to mass of neutrons, which is equal to m, we can take. Then, in such a situation, the total mass of the nucleus m is equal to m into A. A is the mass number, the total number of protons and neutrons. If each nucleon having mass m and we have the number of nucleons is A, so the total mass of nucleus is m into A. Next, go for volume of the nucleus. V is equal to 4 by 3 pi r cube. There, you can substitute the value of r from that formula, so you will get 4 by 3 pi r naught cube A. A raised to 1 by 3, the whole cube becomes A. Now calculate the density of the nucleus. Density is equal to mass by volume is equal to mass is small m into A, mass of each nucleon into mass number divided by 4 by 3 pi r naught cube A. Now I cancel, so that you will get 3m divided by 4 pi r naught cube. Look at this equation. There is nothing related to atomic number or mass number. Here m is mass of nucleon, which is a constant. R naught is a constant 1.2 Fermi. Therefore, we can say density is a constant irrespective of the atom. If any variation related to atom, which will be indicated by the presence of atomic number or mass number in the formula, but it is not there. It's a constant. All these quantities are constants. So you will get a constant. Therefore, we can claim that the nuclear densities are independent of atoms. Okay, for all nuclei are having nearly same densities. And compare it with the average mass density of sodium. Okay, average mass density of sodium will come in terms of 10 power 3. And when you substitute the values and you calculate the density of the nucleus, you will get a density of the nucleus in the order of 10 power 80. While density of sodium is in the order of 10 power 3. So imagine the situation. Usually for our metals, the densities are in the order of 10 power 3. Metals are having high density, you know. Even mercury is having density, the highest density 13.6 into 10 power 3. But instead of 10 power 3, you are getting 10 power 18 so that you can imagine the density of the nucleus. Even we can't lift 1 teaspoonful of nucleus if we can isolate and keep it there. So its mass will be that much high as the density is in the order of 10 power 18. Now, next question 29. A laser source, okay, from there light is sent to moon, and it takes 2.5 seconds to return back. So when you send the light from Earth to moon, it returns back in 2.56 seconds. So that how much is the lunar orbit? Means what is the distance between Earth and the moon? We can use the formula R is equal to C, speed of light 3 into 10 power 8 into T by 2. What is the reason we need to take T by 2? Because 2.56 is the time for the light to reflect back to Earth. So T by 2 you have to substitute, then you can calculate the answer. Then next question 30. Sonar. From sonar we know ultrasound waves can be propagated and can be detected back also. Okay, the time delay between the generation of a probe wave and the reception of its echo after reflection from an enemy submarine is to be 77 seconds. After 77 seconds, the reflected wave reach over the device. Okay, so what is the distance? Again, distance is equal to speed into time. Speed is given there, 1450 meter per second. Again, here also the time is the time to come back, to reflect back. So T by 2 you have to substitute and you have to find the answer. Then question 31. Okay, so we have 3 billion years time is given. Then what is the distance for the light to reach after 3 billion years? So that we can calculate distance. D is equal to speed of light into time. Speed of light is 3 into 10 power 8 meter per second. And it takes 3 billion light years to return back, so that convert light year into seconds and substitute in the formula so that you get the answer for the distance. Now, next question 32. Here, solar eclipse. Solar at the time of a complete solar eclipse, we cannot see the sun because you can see here as shown in the diagram, the disk of the moon will completely block the view of the sun. Okay, so now determine the approximate diameter of the moon. So has to calculate the diameter of the moon. So we can give the, so we have the sun's disk. We can take AB as the diameter of the sun, CD diameter of the moon, and we are observing from Earth here. Here we can use the property of similar triangles. We can see AB divided by CD. AB and CD are similar triangles, so AB divided by CD is equal to B divided by distance between Sun and Earth, divided by D, distance between Moon and Earth. From there, CD can be calculated. CD is the diameter of the Moon. CD is equal to AB, the diameter of the Sun, into D, distance between Earth and the Sun, divided by B, divided by BE. The distance AB is the diameter of the Sun, D is the distance between Moon and Earth, and B is the distance between Sun and Earth. You can substitute the values there, and these values are given in one of the tables inside the chapter. So find out the values of A, B, D, E, and B, E from the table and substitute, then find the diameter of the. So that's all the numerical problems of this chapter. Thank you.